Now that we've taken an intuitive look at conditional probability, let's formalize that and come up with a conditional probability formula. So what we've seen so far is that if we have our probabilities represented in a Venn diagram like this, we're just going to go with kind of a simple case we can. And we have A and B. If we want to work out the probability of A given B, what we did is we restricted our view to just the stuff in B, and we said out of that, what's the probability that it was also A in here? So out of B, that is out of everything that was B, what was the probability that it was also A? So that's this region here divided by all of B. So that's just the intersection, probability of A and B. So that is it. That is our conditional probability formula. Now, in reality, this is a simplified version of something called Bayes' theorem. And Bayes' theorem is an absolutely fascinating topic on its own and demands its own course. Yeah, do check that out because it's super interesting. But this is the kind of smaller version that we're going to be using, and this will be good enough to get us loads of interesting results in the A-level. So that is it, right? Commit that to memory. That is your conditional probability formula. It's useful in that form. You could obviously multiply both sides by probability of B as well if you wanted to make probability of A and B the subject, but this is your conditional probability formula. Just before we launch into a question that involves this, notice that this only works for events which are not independent. So this is only for non-independent events. Now, the reason for that isn't anything like that. It's not that it goes wrong if they're independent. It's just it's super boring if they're independent. Remember, for independent events, probability of A and B is probability of A times probability of B, which means that our conditional probability formula just becomes a little bit daft because it's probability of A and B, which is probability of A times probability of B, divided by the probability of B. But then these just cancel and we just get probability of A given B is just probability of A. So this is for independent events, but think about it, that kind of makes sense. Like take two totally unrelated events, like the probability that I roll a 6 on a dice and the probability that it's raining right now in Tokyo. Well, they're definitely independent. What would you think if I said, what's the probability that I roll a 6 on a dice given that it's raining right now in Tokyo? I mean, it's just 1 in 6. Like it's just irrelevant that it's raining or not in Tokyo. So that explains why if the events are completely unrelated, the probability of A given B is just the probability of A. So this is just to say that this is only interesting for events which are related, that is non-independent events. Okay, let's have a look at some questions. Okay, so probability of E is 0.25, probability of F is 0.4, and probability of E and F, that's our intersection symbol, is 0.12. And here's a ton of questions to work out. Okay, first things first, if it looks like the sort of thing we can represent on a Venn diagram, let's represent it on a Venn diagram. So there are only 2 events for now. I can see another one coming up later on in the question, but for now, we can get this all into one Venn diagram just with 2 regions. So here is E and here is F. And what's our information? Well, the first thing I can write in is the intersection here is 0.12. Okay, now probability of E is 0.25, but that's for this whole region here. So I've already got 0.12, so what's left must be 0.13. Now these 2 things do add up to 0.25. For F, I need the entire F bubble to add up to 0.4. I've currently got 0.12, so what's left is 0.28, and now that adds up to 0.4. Now the outside, let's not forget about that, that's just 1 minus all of the stuff that we've got so far, so 1 minus 0.13, minus 0.12 minus 0.28 is 0.47. So it's 0.47 on the outside. Okay, let's give ourselves a bit of room and try to answer some of these questions. So here is the Venn diagram I made earlier. Right, let's try to answer this. Probability of E given F. So I would always start by writing out the formula here. So probability of E given F is the probability of E and F divided by the thing that's given. So divided by the probability of F. So what is that in this case? Well, it is the probability of the intersection, so 0.12, divided by the probability of F, which is 0.4. And this I think I can just key straight into my calculator. 0.12 divided by 0.4 is 0.3. So there's our answer to that. Next, it's find the probability of not E given not F. So this is a bit of a quirky one. Not E given not F. We'll use the formula. That's the probability of not E and not F divided by the probability of the thing that's given, which is not F. So which part of my Venn diagram is not E and not F? So it has to be not E, it can't be in the E bubble, and it has to be not F, so it can't be in the F bubble. Well, the only bit which is both not E and both not F is this stuff on the outside, 0.47. Now what about the stuff which is not F? Well, not F is everything which is not in here. We could just add these two together, which is 0.6. Maybe the faster way of doing that would have been to say, well, if probability of F is 0.4, probability of not F is 1 minus that, 0.6. Now we've got a calculation to do, 0.47 divided by 0.6, and that gives me 0.783 when I round it to 3 significant figures. Okay, part C, explain, showing you're working whether or not E and F are statistically independent. We should use the formula that I showed you in the Year 12 course and just on the last slide, but I already know the answer is that they're not, because probability of E given F was 0.3, whereas probability of E was 0.25. If they're independent, the probability of E given F would have just been the same as the probability of E. But let's do it the proper way, which is checking to see, is the probability of E and F the same as the probability of E times the probability of F? The probability of E and F is the intersection, it's just given, 0.12. What's the probability of E times the probability of F? Well, that's just the probability of E, 0.25, times the probability of F, which is 0.4. Multiply these things together and we get 0.1. Are they the same? No, they are not. So, 0.12 is not 0.1, and therefore they are not independent. And I have given my reasons, so you don't need to actually write words here. It's a bit of a break, isn't it, in your stats exam? Just do the maths, right? That's what you need to do. That is your reasons. Okay, let's keep going with this question. So the event G has probability of G is 0.15. The events E and G are mutually exclusive and events F and G are independent. Draw a Venn diagram to illustrate this. Okay, so the one that I can represent graphically is that E and G are mutually exclusive. So E and G should not intersect at all. So probably the best way to represent this is to have E over here, and E does intersect with F, we know that, and F is going to intersect with G because, well, they're independent, so they're not mutually exclusive. And this kind of shape should do it, where I've got E, F, and G. And look, I do successfully show that E and G are mutually exclusive. Right, I need to fill this in. So I've already done a lot of this hard work, haven't I? If I flip back, I can see I've got 0.13, 0.12. Right, but I can't actually fill this stuff in yet. So how can I fill in the rest of this Venn diagram? Well, I think I can get this intersection. Why? Because F and G are independent, I know that the probability of F and G, that's the intersection, is the same as the probability of f multiplied by the probability of g. Well, the probability of f we know is 0.4. The probability of g we've just been told it's 0.15. Multiply those together and I get 0.06. I should just check that in case I've made a silly error. Yep, 0.06. So that is the intersection. So 0.06 is my intersection there. So now I can work out what goes in here because f in its totality is 0.4. So 0.4, and I've already got 0.12, so I'll take that away. And I've already got 0.06, so I'll take that away. And it leaves me with 0.22 for this region of f, which is not E and also not G. What about the rest of G? Well, all of G is 0.15, but I've already got 0.06, so I can do 0.15 minus 0.06, and that gives me the rest of G. And now, look, 0.09 plus 0.06 is the 0.15, which it should be. Okay, what's left on the outside? Well, it's just 1 minus everything I can see before me. So 1 minus all of these terms in here gives me 0.38. So 0.38 is the outside. So I think that has now done D. Draw a Venn diagram to illustrate the events E, F and G, given the probabilities for each region. We've done that. Now, question E. Find the probability of, okay, we've got a complicated thing here, F or G, but not that. So not F or G. Well, F or G would be this entire region here. So the kind of combined bubble of FG here. So all of that stuff. So we want not that. So what are the things which are not in F or G? Just this and this. So the probability of not F or G is that plus that, which is 0.51. So 0.51 is the probability of not F or G. All right, so that is conditional probability. That is the formula. We've now just got to see how to apply this in all sorts of novel and exciting ways. So next up is going to be looking at conditional probability applied to tree diagram questions. I'll see you there.